Hello everybody. This video we will wrap up chapter 14. So I'm going to go by what was covered in my 11 a.m. section. If you're in 9 a.m. then you already saw the end of this PowerPoint. So just keep that in mind, but I record the 11, so I wanted to continue with where the 11 a.m. session went off, or left off. Okay, so we had talked about colligative properties of non-electrolytes, right? We talked about vapor pressure reduction, boiling point elevation, freezing point reduction or depression. And this diagram at the end here, so skipping through real quick, this diagram at the end shows a phase diagram for a pure liquid versus a solution. So notice that we have this dark blue area that I'm adding that red line to. This shows that for the solution, so for pure water, if it is a solution, so we have a solute, this is the normal boiling point. And so with a solute, the boiling point is elevated to a higher temperature, right? And so that change is that delta T for boiling. Liquid water has a normal boiling or a normal freezing point right here. And if we were to add a solute, that freezing point is decreased or decreased to a lower temperature, and that change between these two temperatures for the freezing point is that delta T. And so it depends on, of course, what that delta T is. It depends on the concentration of the solute. One other colligative property that we didn't get to in either class is osmosis. Well, it's related to osmosis. And so osmosis is the movement of solvent molecules through a semi-permeable membrane. So a semi-permeable membrane is a membrane that allows some molecules to permeate. Those holes in the membrane are large enough to allow solvent molecules to pass back and forth, but are too small to allow the passage of solute molecules or hydrated ions. So if you had a solution with a semi-permeable membrane, solvent can go back and forth. So we'll talk a lot about water as the solvent. But any particles, if you only had particles on one side, they're staying on that one side. They're not able to move. So I have a couple of conditions here. So if a semi-permeable membrane, so again, some container of liquid with a membrane in between, if you have two identical solutions on either side, then the solvent molecules will move in opposite directions at the same time. So we have solute, let's say we have generally two solute particles per side. Solvent molecules will move in opposite directions at the same time, so they are transferring between the two sides of that membrane, but there is no net osmosis. The concentration of either side is remaining constant, and the only thing that's passing are solvent molecules, but they're also passing at equal rates, so there's no change in the two solutions. If you have two sides of that semi-permeable membrane, where now one side contains a solvent and one side contains a solution with solvent particles, well, on the solution side, so in this case the left side, there are fewer solvent molecules per volume because some of that volume is taken up by the solute, which means fewer solvent molecules pass through the membrane from the solution side than from the pure solvent. So on the solution side, let's use these larger circles to represent solvent. So left side is solution, right side is pure solvent. There are more solvent molecules from the right side, which is pure solvent, passing through that membrane than there are on the left. So this means that solvent, that's a solution, that's a solvent. Solvent flows from the pure solvent to the solution, which results in a net osmosis. So now solvent molecules will move to the left, and there will be additional solvent molecules on the left side. More osmosis, more transfer of solvent molecules from the right side to the left than from the left side to the right means we have a net osmosis. So we can use osmotic pressure or capital pi, Greek letter pi, just to fit in the correct blanks here. There's pi. That can be used to stop the net osmosis. Okay, so what's happening here? So the first picture, we have one side that has pure solvent. Now that's the left side. The right side has solute. Those are the orange particles. Let me switch to my laser pointer here. Okay, so left side, pure solvent. Right side, we have some solute particles. And so there is a net flow to the right where the pure solvent, molecules from the pure solvent are moving to the side with the solute. And what they're doing really is decreasing the concentration on the right side. Okay, so on the right side, the pressure that is exerted on the outside here, so P2, that's less than the pressure of P1 plus that osmotic pressure. And so these are not even. They're not an even volume. When the pressure exerted on that side where solvent molecules are traveling is equal to that P1 plus osmotic pressure, that's when you have the system at equilibrium. Water levels are approximately equal. We have an equilibrium solution. So reverse or osmosis on the left, that occurs when the solvent is flowing into the solution. Now, if you add even more pressure onto that side with the solution, then that will force some of the pure solvent molecules to go back to the other side, and this is reverse osmosis. So this is increasing pressure externally on the solution side, causing pure solvent, because that's the only thing that can travel between this membrane, so that water, in this case, is traveling to the left. We can calculate this osmotic pressure, capital pi, here with this equation. Going back to my pen. So here's our equation. The osmotic pressure is equal to molarity times the gas constant in liters times atmosphere divided by mole times Kelvin, and then times temperature. So you can calculate pressure needed. It depends on concentration. This is molarity of solution. So solute, moles divided by liter, temperature of the solution, and the gas constant. Now, osmotic pressure is usually an ATM because we are using the R value in liters times atmosphere divided by mole times Kelvin. This is molarity in moles per liter. And then temperature in Kelvin, which we have there. Now, a little bit more about reverse osmosis. So this is when pressure is increased on this right side, more pressure is added, that forces pure solvent molecules to move to the left. So net flow is to the left. Reverse osmosis is used to purify water. So if you imagine adding a solution to the right side of this chamber, adding pressure, only allowing water molecules and no solute molecules to move past that membrane, then that forces water molecules to go to the left. And then now on the left side, you have pure water. That semi-permeable membrane, though, right in between, that has to be strong enough to withstand that pressure for this to occur. But this is one method that can be used to purify water. Another example of a semi-permeable membrane, which you may have heard of, is the cell membrane. So cell membranes are semi-permeable, and we'll talk specifically about red blood cells. For a red blood cell in an isotonic solution, note that iso means same. So similar, same solution. What that's referring to is the concentration outside of the cell equaling the concentration inside the cell. These cells are donut shaped. This is isotonic right in the center here. So this is a isotonic solution with red blood cells. In a hypotonic solution, the concentration of solutes in the medium surrounding a cell is lower than inside the cell. So that means that inside the cell, so if we draw a circle, this is the cell, there's a high concentration of solutes than there is outside. So water will travel into the cell to decrease the concentration of the solutes on the inside. And so to reach a concentration on the inside of the cell that equals the outside. And that is shown in this first image here. This is hypotonic. So the movement of water into the cell causes the cell to increase in size, become spherical, and it can eventually burst. So at lower ion concentrations, this is concentration of the surrounding solution outside of the cell. Lower outside of the cell, higher inside the cell causes water to move into the cell. And then the opposite is a hypertonic solution, and this is when concentration of solutes in the medium surrounding the cell is greater than outside of the cell. So higher concentration outside of the cell. So water is going to leave the cell to the area of higher concentration. This is what a hypertonic red blood cell looks like. Water moves from the cell to the surrounding solution, and that causes the shell to shrivel because there's less water in the solution, or in the cell. Okay, let's do a learning check related to osmotic pressure. So we have an aqueous solution with 2.00 grams per liter of a detergent. The osmotic pressure of the solution at 25.2 degrees Celsius is 0.0757 atm. We're looking for the molar mass of the solution. Well, we are given osmotic pressure, so that's a good hint that we'll use the formula here, molarity times gas constant times temperature. We have osmotic pressure in units of atm, so that's good to go. 0.0575 atm. We don't know molarity. That is going to be used later. We'll solve for molarity. We do have R, of course, that's our constant. And temperature is 25.2 degrees Celsius. If you convert this to Kelvin, that's 298.35 Kelvin. And we need to use Kelvin in this equation, so 298.35 Kelvin. Simplifying this equation to find the value equal to m, so taking 0.0575, dividing by R and T, we have molarity is 0.002347 molar. So remember what molarity is. This is moles of solute per liter of solution. So we have 0.002347 moles of solute per 1 liter of solution. Let's say we have a 1 liter solution, then in that solution we have 2 grams. So we can use that conversion. 1 mole per liter. We also know that in 1 liter of solution, there are 2.00 grams of solute. Using this, we can cancel out the 1 liter of solution. Now we have moles of solute divided by grams of solute. This is 0.00117 moles of solute divided by grams of solute. Now usually we report molar mass in grams per mole, so if you take 1 divided by 0.007, or 0.00117, this is 852 grams per mole. So that is the molar mass of the detergent. Okay, this next learning check is similar. You are working with an osmotic pressure for an aqueous solution. You have 50 milliliter solution with 0.383 grams of that solute at 25 degrees Celsius. You'll go through a similar process to solve this one. I've got the answer here, so I encourage you all to try, and then we can cover this in a future recitation or office hours. But we'll move on to this last section of chapter 13. So again, if you are in the 9 a.m. section, we covered the first, just one slide of this. So there is a learning check that I'll do as well. So stay tuned for that. Otherwise, let's talk about these colligative properties of electrolytes. So remember we did 13.4 section was about non-electrolytes. This solution is about electrolytes, which make ions. So this is when you are dissolving an ionic solution, right? Electrolyte solution. They make lots of ions. And so we need to take into account how many ions are generated per ionic solid. Because as you probably remember, if you have, for example, sodium chloride, ionic compound is a solid, dissolve that in water, that dissolves into sodium with a +1 charge and chlorine with a -1 charge. Those are now 2 solutes particles for every 1 ionic solid. So we have a factor that I'll talk about on the next slide that takes all that into account. Okay, so substances that ionize, they make ions, they make more particles in a solution than their own concentration may suggest. So this I here is a factor that demonstrates how many ions are formed per formula unit or per molecule. So let's do some examples. Let's do sodium chloride before we talk about calcium chloride. So sodium chloride as a solid, dissolve in water, becomes sodium plus 1 charge, that's aqueous, and chlorine minus 1 charge, that's also aqueous. For this reaction, its I factor, this Van't Hoff factor, is 2. Let's do another example. Let's do calcium chloride. Solid, ionic solid, dissolved in water, becomes calcium with a plus 2 charge, aqueous, and 2 Cl minus. Its Van't Hoff factor is 3. So this factor accounts for the number of ions generated per 1 formula unit of the ionic compound. Sodium chloride, 1 formula unit, dissolves into 2 ions, so its Van't Hoff factor is 2. Calcium chloride, 1 formula unit, dissolves into 3 ions, so its Van't Hoff factor is 3. It's 3 because there's 1 calcium and 2 chlorine ions per formula unit for calcium chloride. Something like glucose, C6H12O6, solid, so solid glucose. If you add that to water, it does not ionize, it stays as C6H12O6. So its Van't Hoff factor is 1. It stays as 1 particle. So that's why we don't have the Van't Hoff factor for non-electrolytes. They stay as their full molecule. Glucose would stay as its entire molecule, would not separate into ions. So it does not have a Van't Hoff factor because that would just be 1. We don't need to include that. Keep it simple when we can. So for any ionic compound, any electrolyte that dissolves in solution, we have the same 3 formulas for freezing point depression, boiling point elevation, and osmotic pressure. But this Van't Hoff factor is added and multiplied in each of those equations. So for electrolytes, you must include I, that Van't Hoff factor, in these equations. Let's do a learning check. So last slide for this PowerPoint, where we'll take into account that Van't Hoff factor. Now in class I talked about adding salt to boiling water when you're cooking pasta, because that could increase the temperature of water. So let's say we have 2 liters of water at 25 degrees Celsius, and you're boiling that with 15 grams of salt, sodium chloride table salt. The solution's brought to a boil, and we're calculating the expected boiling point of this water solution, sodium chloride and water. One value, well, let's think about the equation first. We're going to use the delta boiling point equation, so change in boiling point. We are working with sodium chloride, which is an ionic compound. You will have to recognize if you have an ionic compound or not. So that's Van't Hoff factor times this boiling constant times molality. Kb for water is 0.51 degrees Celsius per molality. So that would be a given value to you. So we have Kb. we can calculate I, or we can determine I by thinking about sodium chloride. Yes, I have this on the previous slide, but if you're approaching a new problem, you have an ionic compound, you'll have to consider which ions are created and how many are created when this is dissolved in solution. So sodium chloride, we have one sodium for every chloride. So these are aqueous ions. And from this, we know that I, Van't Hoff factor, is equal to 2 because 2 ions are formed for every 1 formula unit of sodium chloride. So we have I, we have Kb. We're calculating the final boiling point. We need to find molality. So molality, mole solute divided by kilogram solvent. So let's find the moles of the solute and the kilograms of the solvent. Well, we have 15 grams of salt. We have molar mass, so we can convert to moles pretty easily here. 1 mole, 58.44 grams. So this is 0.26 moles of sodium chloride are added. And then kilograms of solvent, we have, there's 2 liters of water. Now we're given volume and we need to go to mass. The relationship of mass and volume is density. And density for H2O is 1 gram per milliliter. So we have volume in liters, we need to convert to milliliters. And then use density and then convert to kilograms because in molality we need kilograms of solvent. Alright, so we take liters of water, cancel out liters, convert to milliliters, cancel out milliliters, convert to grams with density, and then convert grams to kilograms with that kilogram to gram relationship. And this provides that we have 2 kilograms of H2O. So this molality, taking these both up here, so I'll use that and this in this fraction, 0.26 mole sodium chloride divided by 2 kilograms of H2O. This is 0.1283 molality, or molal. Alright, so we've calculated molality, we have Van't Hoff factor, we have Kb, we need to find this delta T. Now also remember for delta T, now I'm going back to that original equation, this is boiling point of the solution minus boiling point of the pure solvent, I Kb times M. So boiling point of the solution minus boiling point of pure solvent, boiling point of water is 100 degrees Celsius. This is equal to Van't Hoff factor 2 times Kb, 0.51 degrees Celsius per molality, times molality, which we calculated, 0.1283. Simplifying this, so multiplying everything on the right and then adding 100 degrees Celsius, we have that The boiling point of the solution is 100.1 degrees Celsius. So adding 15 grams of salt increases the temperature by 0.1 degrees Celsius. Now, this was an example with an ionic compound with an electrolyte. The process would be the same if this was a non-electrolyte, except for the inclusion of that Van't Hoff factor. So it's the only thing that is different for this process when we have an electrolyte or an ionic compound versus a non-electrolyte or molecular compound. All right, I'll end the video here. This concludes chapter 13. The next one will start chapter 14.